There we go. Well, I will begin with a word of prayer. I will begin with a word of prayer. All right. Dear Father, we thank you for this day. I don't, again, thank you for these students. I thank you for these students for the first time. Pray that we'd have a good class today and just understand some part of what happened on the test yesterday. In the name of my prayer, Lord Jesus. Amen. So Dr. Sprano has asked me to come in and try to solve your test for you. So odds of me actually getting through the entire test in a Monday, Wednesday, Friday lecture kind of slim, but I'm going to have at it.
Bad thing that he asked you to come in with their test?
What's that?
Is it a bad thing that he asked you to come in with their test?
I mean, I'm not looking at your test. I'm trying to, solve it. Now, I'm recording this in part as a cautionary tale for my section, They haven't had their first test yet, and they don't have a sense of what could happen on the integration test in here, right? So, integral of sinh squared x dx. How would we do this? Personally, if I was facing this, I would say, well, that's 1/2 of e to the x plus e to the minus, minus, right? We square that thing. See, at the moment, I've forgotten the identity for sinh squared, so I'm working it out. So that's apparently aha. So we have 1/4 sinh of 2x minus x over 2 plus a constant. All right. Problem 1 done.
How did you take the 2 in the middle out of innocence multiplication?
Algebra. Minus 2 over 4 is 1/2. What? Was the question? I don't know who. I didn't hear you. I didn't know where that question came from. Yep. You could just take the integrals of the e's, but I prefer my answer in sinh. So, yeah. So next up, now his answer looks a bit different. This is also the same as if you worked out a different way. So Dr. Sprano, in his solution here, looks like he has used integration by parts, which of course you could do. And if you did that, you might have come to the following answer: 1/2 sinh x cosh x minus x over 2 plus a constant. That comes from making a u equal to sinh x and dv equal to sinh x dx, integration by parts. Does that make sense? This could be viewed as u dv. You could integrate by parts. Now, listen, I'm not going to go over 2 solutions for every problem. If I get to 1 solution for every problem, we'll be lucky. So let me go on. But he used integration by parts to do problem 1. Problem 1, part B, we're facing the integral of x sinh squared of x. Come on, sinh squared of x dx. All right, so at this point, integration by parts makes a lot of sense here. So this would be my dv, this would be my u. So of course we have uv minus integral of v du, right? But if u is equal to x, du is dx. If dv is sinh squared x dx, then what's that make v equal to? Right. We could use, I'll go with my answer foolishly, see what happens. Sinh of 2x over 4 There's more than one way to do these, right? Now, so with that, I'll start over here. Only got so much board space here. So we have x times sinh of 2x over 4 minus x over 2, that's my v, minus the integral of v, which was sinh of 2x over 4 minus x over 2 times what? Oh, dx. Oh, and that we can just straight up integrate. So this gives us x over 4 sinh of 2x minus 1/2 x squared. And then this integrates to minus 1/8 cosh of 2x plus 1/4 x squared plus a constant, right? Minus a minus gives me a plus. So, yep. Now, of course, this and that simplify a bit. He'd probably want you to do that, right? So x over 4 sinh of 2x, I'll clean it up just a little bit, minus 1/8 cosh of 2x, and then minus 1/4 x squared plus a constant. Now your answer, of course, would look different if you had gone with the blue answer for part A and followed that with the integration by parts for part B, right? All right. I probably better pick up the pace if we're going to get through this. Part 2A. Ooh. Hey, this one looks fun. I like this one. We face the integral of dx over x squared times 9 minus x squared to the 3/2 power. What should we do? Give up? Well, I mean, yeah, you can withdraw. We offer this course every semester, that's true. How about x equals to 3 sine theta? That seems like a good choice to me because we've got a radical downstairs and it's 9 minus something squared, so 3 sine theta is a good trig substitution to make here. With that substitution, my 9 minus x squared is 9 cosine squared theta. And of course, dx would be 3 cosine theta d theta. Making that substitution here, we have integral of 3 cosine theta d theta, x squared, well that's 9 sine squared theta. And then we're looking at 3 cosine theta, oh, excuse me, I can't follow my math, 9 cosine squared theta, all to the 3/2 power. Now be careful as we simplify that. What do we got? 3 over 9 is 1/3. 1 over 9 to the, what's 9 to the 3/2? 27? Okay. Yeah, I believe. All right, integral of, what do we got here? We got cosine theta d theta divided by sine squared theta. And cosine squared to the 3/2 power is what? Cosine cubed theta, do you guys believe? I believe that. Let's see here. How should we go with this? Get rid of the cosine on top. So that's 81 integral of d theta. And it looks like we got a sine theta, cosine theta squared. I mean, personally, what I would do here at this point is go, okay, so that's 1 over 81 integral of d theta over 1/2 sine 2 theta quantity squared, which will then make this 4 over 81 integral of cosecant squared 2 theta d theta, which is elementary. And so the answer is 4 over 80, minus 4 over 81. And there's a half because of the u substitution, and that's a cotangent of 2 theta plus a constant. What? So you guys are you're not believing that this is true? I mean, I hope you know this.
We can also do, like, symbolic.
This is not like, this should not be novel to you at this point. And the fact that this is elementary should also not be news to you, right? Now, there are other ways to do it. In fact, Dr. Sprano has not done it this way. He has done it with a what? Yeah, he used secant. So let's see here. I'll do, I'm trying not to do things two ways. You guys are ruining my, all right, fine, I'll do it his way. So 1 over 81, what you guys want me to do was what? Integral of what?
Secant squared, cosecant squared.
He rewrites it as secant to the 4th theta over tangent squared. Because he's done a bunch of these in class, I know he's doing this kind of example in here now, yeah? You guys see that? So basically dividing the top and the bottom by cosine to the 4th gives that, right? And the reason to do that is what? One over 81, yeah, integral of, what is that? Secant squared, what is secant squared? So that's tangent squared theta plus 1, secant squared theta d theta, divided by tangent squared theta. Of course, the reason to do that is to make a u substitution of tangent theta. So we got u squared plus 1 over u squared du, making u equal to tangent theta. So du is secant squared theta d theta. And then, of course, we can integrate that. 1 over 81, the u squareds cancel, integrate to u, and then minus 1 over u plus a constant. So we got 1 over 81 tangent theta minus cotangent theta plus a constant. Now, in this sort of problem, we should leave our answer as an algebraic function because we can, right? And what's the algebraic function here going to look like? I'll put the triangle down here. X over 3 equals sine theta, right? So we can look at the opposite side being x, the hypotenuse being 3. The thing we got rid of is the other one, right? 9 minus x squared. So, in other words, the answer is 1 over 81. Tangent theta is x over the square root of 9 minus x squared. And then minus the square root of 9 minus x squared over x, plus a constant. All right. To b. So here we're facing the integral of the square root of 16 x squared minus 25 divided by x squared dx. All right, so let's see here. We make a x equals to 5/4 secant theta substitution. That makes 16x squared minus 25 equal to what? 25 tangent squared theta, I believe. Right, so dx is 5/4 secant theta tangent theta d theta. And so what we're looking at then is the integral of the square root of 25 tangent squared theta. And then my dx is 5/4 secant theta tangent theta d theta divided by x squared was what? 25/16 secant squared theta. All right, well, we should clean that thing up. How do we clean this up? You got the 25 upstairs cancels with 25 downstairs. I think we're left with 4. Integral of tangent squared theta d theta divided by, looks to me like secant theta. So the square root of 25 is 5. 5 times 5 is 25. 25 cancels 25. We're left with 1/4/16, which is otherwise known as 4, right? 4/16 and 1/4. All right. Yeah, sines and cosines, because we've got like an odd number of trigonometric functions here. So sines and cosines seems like a good choice to me. So what you're looking at here is 4 integral of sine squared theta cosine theta d theta divided by cosine squared theta.
Can't you just convert tangent squared to secant squared theta minus 1 and then split up the integral? It would cause problems.
Yeah, if I go this path, then I have to change cosine squared to 1. Yeah?
That first section would be square root 25 times 0 minus 25. Well, just for the square root.
The 16x, yeah. Listen, if I go this path and I make the cosine theta d theta du, then what do I have to do here? I mean, you can do it. It's possible, right? This would make this, you'd have u squared du over 1 minus u squared if we make u equal to sine theta, right? So can you do that integral? I mean, yeah, we can. But I like what somebody in here said in terms of using secant instead. So I'm going to go that path because it seems lazier. There are many ways to do these. So if I do the secant way, that's 4 integral. Tangent squared is what in terms of secant squared? Okay, so secant squared theta minus 1 divided by secant theta. That's not bad. So we're looking at 4 integral of secant theta minus cosine theta d theta, which we can do. Because we know the integral of secant theta, we've worked that out. That is 4 times the natural log of the absolute value of secant theta plus tangent theta minus sine theta plus a constant. And then we can put that in terms of algebraic functions, right? So in terms of algebraic functions, what we got here? Secant theta is what? 4x over 5. So if I make the triangle for the substitution here, secant is what? We think of it as hypotenuse over adjacent, right? So we've got 5 and 4x up here. And then over here we got what? Square root of 16x squared minus 25, which of course is what we tried to get rid of to start with. So with that in hand, it's easy to write this as an algebraic function. 4 natural log the absolute value. Secant theta was 4x over 5. Tangent theta is now clearly the square root of 16x squared minus 25 divided by 5. And then sine theta is what? Sine theta is the square root of 16x squared minus 25 divided by 4x. And then you got a constant. And there you go. Yep.
Shouldn't there be a 4 in front of the sign of the last step, which would make 4x cancel out?
There you go. Yeah. I do need to distribute the 4. That is true. And probably simplifying it, as you just said, is what Dr. Sprano would want us to do. But he's not here, so he can't make me. All right. Ooh. That can be simplified a little bit. Problem 3. Problem 3. I think I need to pick up the pace. Ahem. (3a), the integral from 0 to pi over 2 of tangent cubed x dx. Aha. Now, first of all, what kind of integral is this? A stupid one?
It's an improper integral.
It is not a stupid integral. That is incorrect. Oh, so you call them stupid? Oh, just you.
Dr. Sprano calls us.
I mean, he has called solutions out of the
Bad algebra.
Well, they were.
Let's see here. Integral of tangent cubed. You know, I haven't thought about, see, somehow I haven't thought about integral of tangent cubed recently. How do you do integral of tangent cubed?
Tangent squared to secant squared minus 1.
Oh, that's, yeah, that's not, this is actually not that exciting. Okay, secant squared x minus 1. And then what you got? Tangent x. Well, that doesn't do it, does it? Why is that? That helps? Oh, I got it. I'm sorry, I'm an idiot. Let's see here. That's secant x. I got you. And that's secant x tangent x minus dx minus the integral of tangent x dx. Let me use a little sneaky notation. So this is secant of x, the differential of the secant of x, minus the integral of, well, plus the integral of the differential of cosine of x divided by sine of x. So that gives us 1/2 secant squared of x plus the natural log of the absolute value of the sine of x. Oops, there's cosine x down here. Natural log of the absolute value of cosine of x plus a constant. There you go. Anyway, this is what you guys are going to tell me, which is good. All right, so this is an improper integral, which means that we have to approach what? We have to approach the bound in the correct way, right? So this is, by definition, the limit. Does he have a standard letter he uses? B? Okay. You guys are just making stuff up. It's adorable. Let's see here. Pi over 2 from the what? What direction are from the left, right? We're approaching it from the left. Integral 0 to b of tangent cubed x dx. All right, great. Now that, I'm going to move over here so I have more board space. We've got the limit as b goes to pi over 2 from the left. So now I'm going to use the fundamental theorem of calculus part 2 to simplify this, right? So we have 1/2 secant squared b plus the natural log of the absolute value of cosine of b, and then minus 1/2 secant squared of 0. I I'll put some parentheses here, plus the natural log of the cosine of 0. I don't need absolute values because cosine of 0 is 1. How does that simplify? What is secant squared? What is secant of 0? You really shouldn't be talking to each other right now. It's not helpful to me. Thanks. That is what? That's 1. Natural log of 1, right, which is 0. So that's actually just what? Minus a half? Is this improper? I mean, the question is this limit? What's the behavior of this limit? I don't know without thinking about it for a second here. So we have 1/2 secant squared b plus the natural log of, let's see here, can we drop the absolute value? What's cosine? As we approach pi over 2 from the left of cosine, it's 0. But is it 0 in a positive sense or a negative sense as we approach that? Yeah, I think it's going to 0 from positive values, right? So that means that, logically speaking, I can drop these absolute values and just write it cosine of b, right? Given the limit. And this is just minus a half. So how is this behaving? Oh, yeah, because cosine of b is going to 0, which means that the log of a very small positive quantity is what? Negative infinity. And how about secant squared? Yeah, that's going to positive infinity. So we got infinity minus infinity, which is, we just cancel them out, right? And the answer is minus a half? Good. All right. So that would be bad logic, yes. So how should we simplify this? What do you do with infinity minus infinity? I think it might be helpful to rewrite this as 1 over 2 cosine squared b, right? Because often making a common denominator is the way to resolve this kind of indeterminacy. So I'm going to make a little bit of a jump here and hopefully I'm going to focus on this piece and pull the minus a half out. That may or may not be legit. I mean, if what I have left in here diverges, then I know that the net integral, the net expression diverges, right? Because this finite minus a half doesn't change the story. So making a common denominator, I have 1 plus 2 cosine squared b, natural log of the cosine of b, divided by cosine squared b. I think that helps us because now we're looking at something of what form? Oh, I'm not sure that really helped. I think I made it worse because now this is going to minus infinity, right? This is going to 0. So now I've got something of the type 0 times minus infinity over 0, which is not really an improvement. Fine, I'll look at his solution. Oh. Huh. That's funny. So this is, another way to look at this would be 1/2 tangent squared x minus the natural log of the secant of x. It'd be a different constant, of course, but secant squared is equal to tangent squared plus 1, right? So you can absorb the plus 1 into the c and rewrite it that way, and the minus the natural log of secant is that it's the same antiderivative up to a constant. Now, look, guys, if I had been lecturing this, I might be like refreshed on how to do these. I haven't touched these. We haven't gotten to this yet, so like I'm not full speed on these kind of limits at the moment. I'm making it look harder than it is. It's probably possible to resolve this through straight calculation anyway, but I'm going to go to his answer because I have how he did that, and that way we won't get stuck, okay? All right, so this would be what? 1/2 tangent squared b minus the natural log of the secant of b. And then what happens when we plug in 0? Tangent of 0, 0. Natural log of the secant of 0 is the natural log of 1, which is 0. So the lower limit here in FTC2 doesn't contribute anything. We get to this. Already an improvement over my choice of antiderivative. Then what's he do? All right, so it's infinity minus infinity. So he, oh, sneaky. He takes the limit as b goes to pi over 2 from the left of the natural log. He changes this to a log. How would you change this to a natural log? Very sneaky. So we can, use this identity because the tangent's positive, so I can do that. Well, and then what do you got? We can use properties of logs. That's the natural log of what? E to the 1/2 tangent squared b divided by secant b. Now the thing inside the log, what's that? That's tangent goes to, that's a really big. Hey, that's infinity over infinity. I like that. The thing inside the log is infinite. We can use continuity of the log to pull the log out of the limit, right? So this is the log of the limit, assuming that the limit exists. If it doesn't exist, we can make sense of it. I'll write this as exponential, so it's easier to read. Let me call this thing star. By L'Hopital's rule, oh, I'm sorry. Come on, get out of there. I said get out of there. That's really screwed in there. Come on. It's like they knew I was going to, oh well. There you go. Let's look around. So by L'Hopital's rule, on type infinity over infinity, what do we got here? So I differentiate the top, what's that give me? Something weird, exponential of 1/2 tangent squared b. Derivative of tangent squared b is what? 1/2 times 2 tangent b secant squared b divided by what? Secant tangent, right? Hey, I think we're finally going to put an end to our suffering here. So, cha-cha, cha-cha. And that leaves me with infinity times 0. No, wait a minute. What's secant go to? Infinity times infinity, I like, because infinity times infinity is infinity. So to infinity and beyond, let's see here. I mean, the point is that this is infinite, yeah. And consequently, star is infinite, which means we're looking at the log of infinity, which is infinity. So yeah, this one diverges. There are probably other ways of showing that divergence than what I just did, but there's a way, all right? Where? Sorry, guys, I've lost track of which pages I've gone through here. Oh man, I skipped this perfectly good. I'm not used to the way he labels problems, and now that I've got the sheets out of order, I'm not sure which one this is. But you'll recognize it. Integral of x plus 5 dx over the square root of x squared plus 4x plus 7. How should we do this one?
Complete the square and the square root of square.
Complete the square. Sounds like a good opening move. Oh man. Duh. So stop. Let's see here, x plus 5 square root, and I will go ahead and complete the square. We've got x plus 2, quantity squared.
Is that a negative x squared over there?
That's just junk. You guys took this test, right? Let's see here. 4, that adds 4, so we had, looks like a 3 there, right? U sub. I don't know, personally what I would do here is x plus 2 dx over square root of x plus 2 squared plus 3 plus integral of 3 dx over the square root of x plus 2 squared plus 3. At this point, I would make a u equal to x plus 2 quantity squared plus 3 substitution. That would give me a du. 1/2 du equal to x plus 2 dx. And over here, I would make a x plus 2 equals square root of 3 sinh substitution. See, because then x plus 2 squared plus 3 would be 3 times 1 plus sinh squared theta. Excuse me, sinh squared theta plus 1. What's sinh squared theta plus 1? Yeah, cos squared theta. And so that would give me integral of 1/2 du. Excuse me. It would give me the integral of du over 2 root u plus 3 times the integral of root 3 cos theta d theta divided by the square root of 3 cos squared theta. Of course, then the cos's cancel. In fact, this whole thing just gives me integral of, well, d theta. So I get square root of u plus 3 theta plus a constant, which is the square root of x squared plus 4x plus 7 plus 3 times the inverse hyperbolic sine of x plus 2 over the square root of 3. Now, you know that the inverse hyperbolic sine of x is the natural log of what?
Most definitely have not covered.
You haven't covered that yet? All right, well then, I'll leave that to him. You can convert the inverse hyperbolic sine to the log of an algebraic function. So this can be rewritten as like a natural log of a particular thing. If you go a different path, this becomes the natural log of the absolute value of the square root of x squared plus 4x plus 7 plus x plus 2 divided by the square root of 3. And there's a 3 out front. Yes, sir?
Why didn't you just use tangent instead of hyperbolic sine?
Because if I use hyperbolic sine, then there's no integration to do. Yeah. When's the 8:15 class end? Oh, okay. Good. Good. I still have time. Any integral that you can do with a trig substitution, you can also possibly do with a hyperbolic substitution. And sometimes the hyperbolic substitution is easier. I mean, basically the point is the derivative of inverse hyperbolic sine is 1 over the square root of x squared plus 1. So if you see 1 over square root of something squared plus 1, it's going to be just inverse sinh as an antiderivative. This one here, 3 to infinity, ooh, fun, minus x squared plus x plus 9 over x cubed plus 3x dx. So, of course, this is improper, right? And so it's going to be the limit, what? I'll say t goes to infinity of the integral from 3 to t of, let me rewrite that, 9 plus x minus x squared and x cubed plus 3x dx. How do you do that integral? Partial fractions, I heard a vote for partial fractions, very good. And so that's x times x squared plus 3, yeah? So partial fractions here looks like a over x plus bx plus c over x squared plus 3. And if you go through the steps there, we don't have time obviously, you will get minus 3 over x plus 2x plus 1 over x squared plus 3. So with that in mind, we have the limit as t goes to infinity. If you do the integral, we've got minus 3 natural log the absolute value of x plus the natural log of the absolute value of x squared plus 3 plus 1 over root 3 inverse tangent of x over root 3, I believe. Take that whole thing and evaluate from 0 to t, 3 to t rather. Simplify the logarithms. Let's see here, indeed. So this gives us the limit as t goes to infinity of the natural log of where'd the 3 go? Oh, x cubed. I missed that it's x cubed. Natural log of x squared plus 3 over x cubed. 1 over root 3 inverse tangent of x over root 3. I still haven't evaluated yet, guys. Anyway, I'm just going to skip a few steps here. Eventually, you get to 1 over root 3 pi over 2 minus the natural log of 4 over 9 minus 1 over root 3 pi over 3. To get to that, actually, I don't think there's even, it's just an algebraic simplification and limits. There's no even L'Hopital's rule or anything like that. So, and then finally, the last page, we have find the volume of the solid of revolution under natural log x over x from x equals 1 to x equals to e, rotated about the x-axis. So x equals to 1, x equals to e. I don't know what this thing looks like. I don't really care. I'm just going to trust that this problem makes sense. At the moment, you don't have a lot of time to do any soul searching. And we're supposed to find the volume of the solid of revolution formed by rotating it around the x-axis, right? So I think I would probably use washers here, yeah? Washers. So I'd think about, so the thickness would be dx. The volume of that little slice would be pi y squared dx, which in this case would be pi natural log of x quantity squared divided by x squared. The volume then should be the integral from 1 to e of pi natural log of x quantity squared dx over x squared. How do we do that integral? Parts? That seems right. What's my u? U is what? Log squared? That does not, well, try it? All right. Like, try it. You like it. If I do that, then du is 2 natural log of x dx over x. And dv is pi dx over x squared, which means that v is minus pi over x. All right. So I've got minus pi natural log of x over x squared evaluated from 1 to e plus pi let's see here. Integral from 1 to e v du, right? So pi over x times 2 natural log. Oh, so we had to integrate by parts again. Or no?
Is your u v correct? Should be negative pi ln of x quantity squared.
Well, somebody here told me to make u equal to log of x squared, so I was listening and following that, and
And then you use parts again.
That's what you do, but is
That all looks right, but you do parts like twice per meter, or you sub, might be you sub, I don't remember. I think I ended up with ln of x over by x.
all right, well, in any event, that works out to pi times 2 minus 5 over e. So, and And yeah, we just had to integrate by parts again on what I had, but I don't have time, so I think it was just that, looking at his work here. And that was your test. So, yep. Actually, this is somewhat irrelevant to my section because we haven't gotten to improper integration yet, so anyway.